Let's solve this differential equation proof step by step. We'll start with the given equation and transform it through several steps to reach our target equation. Let's begin by transforming the equation to isolate ln y. First, we take the inverse cosine of both sides. This gives us 1 over m times ln y equals inverse cosine of x. Next, let's multiply both sides by m to isolate ln y. This gives us ln y equals m times inverse cosine of x. Now we can solve for y by taking e to the power of both sides. This gives us y equals e raised to the power of m times inverse cosine of x. We'll call this equation 1. Let's find the first derivative with respect to x. Using the chain rule, we get y sub 1 equals e to the power of m times inverse cosine of x times m times negative 1 over the square root of 1 minus x squared. We can simplify this expression. Notice that the first term is just y from equation 1. So we can write this as the square root of 1 minus x squared times y sub 1 equals negative my. Let's square both sides of this equation. This gives us 1 minus x squared times y sub 1 squared equals m squared y squared. Now, let's take the derivative of both sides with respect to x. Using the product rule on the left side and the chain rule on the right side, we get 1 minus x squared times 2y sub 1 y sub 2 minus 2x y sub 1 squared equals 2m squared y sub 1. Finally, let's simplify this equation. Dividing both sides by 2y sub 1, we get 1 minus x squared times y sub 2 minus x y sub 1 equals m squared y, which is what we wanted to prove. And there we have it. We've proven that 1 minus x squared times y sub 2 minus x y sub 1 equals m squared y. This proof demonstrates the power of calculus in transforming complex relationships into more manageable forms.